Welcome to this public meeting for Prairie Rose Lake. My name is Jeff Burkus. I'm the TMDL Program Coordinator for the Iowa DNR. Joining us in a little bit will be Andrew Frana. He's the project lead for Prairie Rose Lake, and he'll be doing most of the talking today. The purpose of this public presentation that we've recorded is to try to explain the document that's available on the Iowa DNR's website. And one of the things that this is going to be important for is to explain a few concepts, and if you have any comments or concerns about the document, you can put in a public comment, and that public comment period runs through September 8th of this year. And so if you do have any public comments, please send those to me at my email address by September 8th. That email address is jeff.burkus@dnr.iowa.gov. I'm going to go through a couple of slides to just kind of set the stage for Andrew and then let him do most of the talking here today. And so a couple of things that we wanted to talk about is just some basic terminology that is really important for our program. The first definition that I wanted to talk about is the word watershed. So to help us do that, I pulled a map from the document, and Andrew's going to be showing this here in a little bit as well. This is a watershed map of Prairie Rose Lake. And so what you want to focus in on here is the section of the map that's clearer or a little bit more well-defined in this colored area. It's outlined here in this dark black outline, and then outside of it is a little bit more gray shaded. So anything inside of this black outline is the watershed for Prairie Rose Lake. The best way to think about this is that anytime it rains, if a drop of rain falls inside of that black outline, it's going to eventually find its way and drain to Prairie Rose Lake. Anything outside of it, so if it falls up here in this upper left-hand corner of the map, that's going to go somewhere else. It's just not part of the Prairie Rose watershed. So we're most concerned about everything and all the activity that happens within these boundaries. So that's a watershed. And we use that map a number of times throughout the document, and I wanted to pull one in here just to show you. You still have that same outline, but now we have very different colors. And one of the things that you'll want to do is you want to utilize these legends that are in all of these maps to give you an idea of what it is that we're talking about. And so for this particular one, this is a land use map. And so all of these different colors are coded in a way down here, and they tell you what's going on. So the majority of the watershed area for Prairie Rose Lake is this yellow and brown cross-hatched area. And then you go down here, and that says, oh, it's row crops. So this area here is used for row crops. And you can see there's a lot of other different colors that give us an idea of what the land is used for in this watershed. A couple of other things that I think are important to note when you see any sort of map is that we'll always give you a compass rose so that you can find your north direction and all other directions. We'll also use an inset map here of the state of Iowa with a little marker of where we're at in the county. And then we'll also give you a scale. So the scale down here will give you an idea of just how much space is in this Prairie Rose watershed. This map here is a little bit more focused in. So this outline here is that watershed boundary that we talked about, but now we're zoomed in just on the lake. But this should give you a pretty good idea if you were to bounce back and forth between these maps. We still have this big watershed area. We're just zoomed in here closer on the lake itself. And in this particular map, where you can go, what is this gold line here that we're talking about? Well, we come down here and that's the public land, marked public land here. That's just the state park. And so that's good resource to have here, but remember, just keep in mind that we are still in this watershed map, and that's shown by this outline here. The next couple of terms that I think are important for us to talk about, the next one would be impairment. So anytime you hear that term impairment, basically all we're meaning is that there are water quality expectations that are not being met. And basically we have what are called water quality standards. And these are measurements that we take and compare against our water quality monitoring through a process through the 303D list, which is the impaired waters list. Now, if you're on the impaired waters list, all that means is that there is some water quality standard that's not being met, some expectation that's not being met. And that's what we have here today with Prairie Rose Lake. And Andrew's going to talk more about the specifics of the impairment and what's happening. The next term that I wanted to talk about is point and non-point source pollution. Point source pollution, a lot of people like to think about that as that you can point to it. A lot of times people say, well, it comes out of a pipe. That's not the most accurate definition, but that gives us a really good start. I like to think of point source pollution as anything that is a permitted discharge into the watershed. And so if there is a permit that allows discharge into the water of the state for that particular pollutant, then that would be a point source of pollution. Now, in this lake, we do not have any point sources of pollution, so we don't have to worry about that term. We are interested in the non-point sources of pollution, which is basically encompasses everything else. Anything that's a source of the pollution that we're concerned about that's not permitted, that's non-point source pollution. You can think of it as runoff from cropland or from forest land. Those are non-point sources of pollution. The last point, the last terminology that I wanted to talk about is just this word TMDL that I've already used a couple times. So a TMDL, I like to think of it as with this picture here, with this pack mule. And so TMDL stands for total maximum daily load. And I've always really liked this picture here because if you think about this pack mule here, this poor guy that's up in the air, at some point he was fine. We have no boxes on this cart. He's able to run around and be able to carry that cart and do his job without any issues. We put a box or two on there and he's still fine. It's getting a little harder to pull around, but it's okay. At some point it gets so heavy that the pack mule can't do anything. And then of course we're at this kind of ridiculous level where there's so much weight on this cart that he's tipped up in the air and he can't do anything. And so the way that I like to think about this is the tipping point. How many boxes do we need to pull off that cart until he can get back on the ground and run around and be able to do his job? And if you think about this with water quality, if we imagine that our lake is the pack mule and the cart is full of boxes of pollution. And so at some point the lake can handle a few boxes of pollution, no problem. But when we put too many boxes of pollution onto that lake, it tips up in the air and it's not able to do its job. And so what we're trying to do is we're trying to find that tipping point for the lake to be able to understand how many boxes of pollution that we need to pull off of that to be able to have the lake function like it's intended to. And so think about this as a specific number, and it's what I like to call the tipping point number. And so the total maximum daily load, or the tipping point, we will also include within the document an implementation plan. Now this is not prescriptive, but rather a plan of ideas that should be incorporated at the local level based on local conditions and what is palatable to the local community. And with that implementation plan and the math, that tipping point aspect that we talked about, those two things combined are what we call the water quality improvement plan, which is what we're presenting today. And then I wanted to show one chart that Andrew's going to be talking about a little bit. And I'm going to let Andrew do the heavy lifting, and I'm going to let him talk about this chart. But I just want to make a general comment about anything that's in the document or anything that we're going to talk about today, is that there's a lot of information that's packed onto these slides, that's packed onto these graphs. And so just take your time, pause, rewind if you have to. Let Andrew explain it to you multiple times with the rewind button. There's nothing wrong with that. I've been working with this stuff for a long time. I still have to kind of take my time to realize what it is that we're talking about. And a couple of tips for being able to do that. The first thing you always want to do is you want to look at what's being said along the axes. So along this axis here, well, we've got years. Okay, so we're going through time here starting in 2002 all the way through 2016. And on this axis, we're talking about something called TSI values. And I'm going to let Andrew explain to you specifically what that is. And then we've got this red line. I'm sure that's going to be important. And then we have all of these different shapes and colors of boxes that relate to this key up top. And so there's a lot of information just to take in with how this map is, or how this chart is set up to begin with. And that takes a little bit of time for you to process, be able to understand completely what it is that we're getting across. And so I would just advise everyone to just kind of take their time with anything like this and be able to really process what it is that Andrew is getting across here. So with that, I'm going to hand it off to Andrew, and he's going to get into the specifics of Prairie Rose Lake, and then I'll come back at the end and wrap up.
Thanks for that introduction, Jeff. As he said, my name is Andrew Frana, and I'm the project lead for Prairie Rose Lake. I'll be talking to you about several things today. We'll start with the outline. First, we'll discuss the water quality improvement plan, what that is and what goes into it. Jeff detailed a little bit how it combines several aspects. Then we'll go into the description of Prairie Rose Lake itself, and then also its watershed. And we've heard earlier what a watershed is and what that means for Prairie Rose Lake. We'll talk about some of the different values and different characteristics of the watershed. From there, we will talk about the actual water quality assessment and how that relates to water quality expectations for Prairie Rose Lake. After that, we will talk about the TMDL development, or how do we get to that tipping point number, as Jeff so artfully described. And then we will talk about a suite of implementation planning techniques that we may be able to use to get our water quality in Prairie Rose Lake back to where we want it. So of the water quality improvement plan, there are several things. First of all, we actually have to go out, monitor, and assess the water body. We have to collect samples, send them to a lab, and see how it compares to what we expect for water quality. If our water quality is determined to be impaired, we will then draft this water quality improvement plan, which does several things. It will determine where the pollutant sources are coming from. It will find that tipping point value, or that total maximum daily load, and then include an implementation plan for locally led solution planning that can help improve the water quality. We are today at step 3 with a public meeting and presentation. We will ask for public review and comments, not only of this presentation, but also the main document that describes the water quality improvement plan for Prairie Rose Lake. And after that, we will hand this off to locally involved parties to see if they can take that next step to implement strategies and practices that may improve water quality. And then of course, we'll have to continue monitoring the lake to see if our expectations are met. So first up, we'll have a map of just Prairie Rose Lake. You can see that it's highly dissected, or it has several different arms and branches that they collect water from various parts of the watershed. Some stats about the lake itself: it has a max depth of 25 feet, an area of almost 200 acres, 196, and then a fun fact, the volume of 1,653 acre feet. If you take that and put all that water into an 80-acre field, you're going to be at over 20 feet of water. So that's quite a bit of water there. But we can see that we have 3 main arms, some smaller areas where water collects before the main body. And then you can see parts of the park itself, highly forested, some small roads and campgrounds. So we know what a watershed is, but let's talk about some details of this watershed for Prairie Rose Lake. It's in Shelby County, about 6 miles southeast of Harlan, so Harlan would be up here. It is part of the east branch of the West Nishnabotna River. So if you can imagine that river having its own watershed, the watershed for Prairie Rose Lake is inside of that watershed. The total area of this watershed, this black outline, is 4,655 acres. So if we compare that to the lake itself, the ratio of land to water is 23:1. Now what that means is for every 1 acre of lake, there are 23 acres of land. So when we start talking about pollutant sources and allocations, things like that, it's definitely important to see what's going on with the land to go ahead and then try to improve things going on in the lake. So next up, we have our land use assessment for Rose Lake. Several things. This legend describes various land uses in the watershed. The yellow and brown striped area is row crops, so that can either be corn or soybeans depending on the year. Since we have a multi-year assessment, we combine those. And then other land uses are farmstead with the red, pasture areas, small pasture areas, grassland and riparian places that are described in more detail in the main document. Then we obviously have roads and the state park area. And these are all described in more detail in the main document itself. But two takeaways, 80% of the area is row crop. So depending on the year, it's either corn, soybeans, or mix of both, depending on what fields you're looking at. And then actually, most fields are terraced. So the main document, again, describes what terraces are. But if you can imagine hills cut out and flattened on various parts, it helps in the long term with erosion and runoff. And that will be described in detail a little bit further. So we talked about land use. Soil type, if you look at the map here, there are several main soil types. The main ones are marshal with this olive color and this complex here in green. Some main takeaways here are the soils of the Prairie Rose Lake watershed are very deep and well drained and come from a loess background, which is windblown sediment, and have uplands and terraces. And this is all important when we start talking about erosion and pollutant sources in the document. So these are just the main takeaways for the presentation. So we talked about land use and soil. Let's look at slopes here. Prairie Rose Lake is very unique in its formations of, I want to use the word interfluvial, but I'm just going to say highly dissected or very heavily sloped areas. So the legend here shows several different classes ranging from class A to class F, depending on how steep the slope is. Going from green to red, the more red it is, steeper the slope. So we can see these areas of almost alternating red and yellow and green stripes here in that row crop area. If you can imagine a terrace being part steep back slope, part flat front slope where the crops would be, these are those formations that you see. And if we look at the percentages, we can see that nearly 60% of the watershed is either moderate to or strong slopes. So if you look down here, the document describes it, but that's either between 5 and 15% slope. And that's fairly heavy compared to what you would see in central Iowa watersheds or other watersheds in the state. And we said some of the row crops were terraced, but not all of them. So non-terraced areas are going to be especially susceptible to erosion or the removal of soil from the topsoil, depending on where you are with land use, soil type, and slope. So that's why those three are mainly important, and they're described in more detail in the document. So we've talked about the Prairie Rose Lake itself, Prairie Rose Lake's watershed, and some of the main characteristics of that watershed. But now, what is the issue with Prairie Rose Lake? What are the water quality expectations that are not being met? So if we look at water clarity, or how clear the water is when you look down at it, Prairie Rose Lake has two main issues, and they stem from algae and sediment. So when we talk about that further, those are the main things that we'll be looking at. So when we assess Prairie Rose Lake, we have to monitor it somehow. So this is actually us getting out onto a boat around here, zipping down here to the right near the outfall where the deepest point of the lake is. Every time we go out there to collect samples, it's the same location. We'll do the same tests. So we'll test for dissolved oxygen, we'll test for pH, we'll test for different nutrient levels, and we'll do that the same times each year. And we do that so we can have a really robust data set with high confidence in those values. So this is just a photo taken from the water quality and water monitoring branch of the DNR. You can see this is just us in action out there taking samples. So when we talk about water quality analysis for Prairie Rose Lake, what defines poor water quality? Well, it can either be too green from too much algae in the water profile, or too murky from turbidity, or just, if you can think of suspended sediment or tiny soil particles that are just hanging out in the water profile. And when we look at Prairie Rose Lake, we see that depending on the time of the year and depending on what's going on in the watershed, It can either be too green, like split pea soup, or too murky, like chocolate milk. And how we determine that, one of the tests that we do when we're out there on the boat is we use this tool called a Secchi disc. The Secchi disc has alternating quadrants of black and white that is attached to a tape measure rule that is lowered into the water. So if you can imagine this Secchi disc being lowered into the water, gradually you're not going to be able to see it anymore, depending on if it's too green, too murky, or whatever. The farther down that Secchi disc goes, the clearer the water that you can see it. If it's up here and you can't see it anymore, then that distance is called the Secchi depth, and we'll measure that and we'll compare it to other depths throughout the year and throughout the assessment period to determine if the water quality expectations are not being met and if it's getting worse or getting better or what have you. All right, so we have our water quality analysis. We have everything talked about the lake and the watershed. Let's go on to some data. All right, so Jeff set me up a little bit here. Before I start talking about the actual data points, let's just look at this chart. The bottom axis, or the x-axis, goes from 2002 to 2016. So that's what we call our assessment period. That 14-year assessment period is talked about heavily in the document and will be the main time period when we start to look at trends and water quality expectations. The y-axis right here will be listing TSI values, or trophic state indice values. So that's just a fancy term for how productive are various quantities in the lake. So for example, is there a lot of vegetation going on in the lake? Is there a lot of suspended sediment in the lake? Is there a lot of nutrients in the water column? So those are three main values that we're looking at. But TSI values, you just can think of the higher the value, the worse the water quality. The lower the value, the better the water quality. And we have this line here of 65. So Jeff talked a little bit about lakes being impaired and water expectations not being met. So when we show this water quality data, anything that's above this impairment limit of 65 would be times when the water quality expectations are not being met. Anytime the data values are below 65, that's where we want to be. All right, so we talked about the assessment period, the TSI values, and what that means. Let's throw some data up on there. So we have three main data points that we're looking at. They're explained further how they relate to each other in the document. But we talked a little bit about Secchi depth. So these blue diamonds relate to how deep that level is once for water clarity. You can look over time. These Secchi depth TSI values tend to range anywhere from just under the impairment limit to just over. And you can see at the end of the assessment period, we have most of them, all of them, underneath that impairment limit. Next up are these green triangles, which track chlorophyll A. So chlorophyll A, think of that more in terms of plant life. Chlorophyll A is a stand-in for algae in this case. And as we know from some of our early science classes, algae is basically a small plant. So we look at how much algae is in the lake at any one time. So you can see again that these values track above and below the impairment limit. And trends are discussed more in the document. So we have how good is the water clarity, how much algae is in the water column, and then trophic state index for TP. Now, what is TP? In this case, it means total phosphorus. So if you can imagine nutrients like you would put on your field or your yard, eventually in the watershed, those would make their way to Prairie Rose Lake. So we can track the level of nutrients in the lake by tracking the level of total phosphorus. Again, those purple squares trend to be above the impairment limit most of the time, getting down here at the end of the assessment period. One takeaway that's described further in the document is this gap here. Around 2012, there were some renovations to the lake that we can see hopefully some water quality improvement of the expectations there, and continued monitoring hopefully will bear that out. So we discussed earlier that the TMDL is a fancy acronym for finding the tipping point of where water quality expectations are not being met. There are several things that go into that. First of all, we have to have a target. What are those packages on that cart that the pack mule can't carry anymore? What is that pack? What are those packages and what is in there? Sources, we want to find out what is the actual source of the pollutant. And then we will look at where those sources are coming from in the watershed. And then we'll actually have the equation or that number value of that tipping point. From there, we can show where the allocation of that, the amount of pollutant is to go to the next step of implementation planning and improving water quality. So without further ado, in this case, the target is phosphorus. We looked at that chart. It's going to come back and be important. So phosphorus in this case can do several things. It can cause excess algae. So if you just think of phosphorus being a nutrient and algae being plants, it makes sense that more nutrients will cause more plant growth. And also phosphorus, when it binds to small soil particles, can create cloudy water because of the excess sediment that also has bound phosphorus to it. So phosphorus is transported by surface runoff and groundwater flow to the lake, causing those two issues. So what we're going to want to do in just really quick terms would be to reduce sediment runoff into the lake to reduce our target of phosphorus. We talked about our target. Let's talk about our target sources. Jeff set this up earlier, talking about point sources and non-point sources. Point sources being anything with a permit that is allowed to discharge or anything that you can point to. And non-point sources would be anything else. So within the Prairie Rose Lake watershed, these are some types of point sources. These all stem from various wastewater treatment plant discharges and things like that. And what we find in the Prairie Rose Lake watershed is that there are no point sources. So it's not something that we will be looking at. It's not something that will be taken into account in the TMDL equation. And that's described further in the document as well. So if we go from point sources to non-point sources, that shows that all of the pollutants, phosphorus coming into Prairie Rose Lake are these non-point sources. And these are just some types of non-point sources. But what we're going to see in the document is that land application of fertilizer and runoff tend to be the main driver of phosphorus pollution into Prairie Rose Lake, causing those water quality expectations to not be met. So when we're talking about what a TMDL is, we talked about our target being phosphorus. We've talked about our sources being non-point. And now let's actually go into the equation, that budget or that tipping point that shows where water quality expectations would not be met. If you can just break it down into a simple equation that's, again, explained it in more detail in the document, we have the sum of WLA or waste load allocation plus the sum of LA or load allocation and MOS or margin of safety. So again, these components are point sources or waste load allocation, non-point sources would be load allocation, and then that margin of safety we put in there just in order to be conservative with our values and ensure that we have a little bit of padding to make sure that we meet those water quality expectations. We don't want to go above that. We'd rather be just slightly below just to give us a little bit of cushion. So the main takeaway, if we put numbers to these values, we can see that again, there are no point sources. So our waste load is 0. Everything else is going to be our load allocation, which the document shows to be 1,868 pounds of total phosphorus per year, TP total phosphorus. And then we have a margin of safety of 208 pounds of total phosphorus per year, giving our TMDL or tipping point value of 2,076 pounds of total phosphorus per year. So what that means is any amount above 2,076 pounds of phosphorus per year could contribute to water quality expectations not being met. If we have that below, then that may indicate that water quality is improving or has been improved. Now, if we compare this to what's going on in the lake right now, our existing load of total phosphorus per year is 3,988 pounds of phosphorus. And if we compare that to our TMDL of just over 2,000, we can see that in order to meet those expectations, we're going to have a 48% reduction of phosphorus to the lake. Now that seems like a lot, but compared to other lakes and other systems, this is a highly manageable goal, depending on what happens in the watershed in the future. So we've talked about our target of phosphorus. We talked about our sources being non-point. We just had our equation. And in order to be useful, let's just throw in some allocations about where that is coming from. And no surprise, if the row crop area is 80%, we can see that it makes sense that the pollutant source of phosphorus would be about 80% as well. So row crop sources of phosphorus contribute to 80% of the total phosphorus to Prairie Rose Lake. All other values, whether that's groundwater or urban sources or forest, are that remaining 20%. All right, let's talk about implementation plan. What can we do to improve that water quality to hit those expectations? So we want to have solutions. We want to, encourage local participation, and we want to allow for future monitoring. So first up, land management or preventative practices. So when we look at that phosphorus eventually making its way through the watershed to the lake, we want to prevent it, first of all, from even leaving the watershed. And that can actually provide benefits to both soil and water quality. If you can imagine examples of these, conservation till, no-till, cover crops, things like this, what they all have in common is their main goal is to try to, in regards to phosphorus transport, is to try to stop that phosphorus from even moving. And if we just take a look at one sample, no-till farming, we can see that this is beans planted over corn from the previous year. And the corn stover that's left in the field has the benefit of not only increasing organic matter to the soil, which can help absorb rainfall, but also the corn stover protects the soil itself by if you can imagine rainfall dropping and it hitting the corn first before the soil, that soil might not become detached, and that detached soil might not make its way to the lake. And with that detached soil might come phosphorus. So the main goal of this in regards to total phosphorus would be to not have the soil even move. Next up, we'll look at structural or mitigation practices. So if we can imagine that soil and that phosphorus starting to make its way to the lake, how can we intercept and trap those pollutants during that transport? How can we slow it down? How can we stop it? How can we mitigate it from coming to the lake? So some examples of that are terraces, grassed waterways, sediment basins, and wetlands. And I want to talk about terraces for a second here in this watershed. Like I said earlier, and how it's displayed in the document, over 90% of the row crops are terraced, but some of these terraces are over 20 years old. So it may be a large benefit to go back, look at those, see if they can be improved, and improve their efficacy to when they were first built. An example that I like to include besides terraces here are looking at a sediment basin. And why I include this one is because it's so immediate that you can see that if you can imagine this runoff coming down the hill of the watershed into this basin, what happens is this water collects here and slows down, and the heavier soil particles fall out of solution and are retained here before they make their way to the lake. So when we back up water before the lake with these sediment basins or wetlands or things like that, that phosphorus-laden soil can fall out of solution and prevent that pollutant from coming to the lake. Our last type of best management practice are remediation practices, and these are meant to fix existing issues in the lake. So if after trying to prevent and try to mitigate phosphorus from getting to the lake, we still see issues with our water quality expectations, we can go in there and actually fix some issues. And some examples of that are fisheries management, or if you can imagine taking control of some of those rougher carp species that can stir up the soil on the bottom and resuspend that phosphorus. Shoreline stabilization, so That can be adding riprap or jetties or things like that to the actual lake perimeter to slow down wave action from eroding soil. And then also targeted dredging. So that's actually going in there with mechanical processes to remove soil, remove phosphorus from the bottom of the lake. And the document describes some of those renovations that took place about 8 years ago, and how much money was spent and what they all did. And we can see from the slight improving trend of the water quality that they may have some benefit. After all that, we have some next steps. We have to continue to monitor. So even though the assessment period for this document stopped at 2016, we want to still monitor 17, 18, 19 this year as well to see, is water quality improving? Are we meeting those expectations? And what else can we do? And in order to be successful, we need local involvement. We need people on the ground that care about this to promote awareness. Some things they can do: create watershed groups, maybe watershed management plans, things like that, that can open up grant avenues. To just, the main goal would be to improve water quality for everybody that lives and recreates in that watershed. And then the DNR, depending on resources and time, may be able to offer technical assistance on these locally led efforts. So after all that, I'm going to kick it back to Jeff, and thank you for listening.
Thanks, Andrew. I just wanted to reiterate what we talked about up top, that if you have any public comments, that those are due to me by September 8th, and you just want to send those to my email address that is listed there. If you want to call and have a conversation about anything specifically, you can feel free to call me. If you have specific technical questions regarding anything with the modeling, Andrew is going to be a great resource. His number is listed there, and his email address is listed there as well. Again, if at any time you have any questions, please reach out to us. We will reply to all of the comments that we receive, and we will include those at the back of our document, and then we will submit that to the Environmental Protection Agency for approval. Thank you for your time, and again, let us know if you have any questions.